Getting more and more boring. I think it's something with the way I select papers. Anyways, hello and welcome to the second edition of Physics Recap, where I talk about 5 papers from the previous month, in this case February, and try to teach you something I learned 2 days ago vicariously through these papers. So welcome back. Please do all the engagement thingies like liking, subscribing, and leaving a comment. I am always open to covering papers that my viewers submit because it means I don't have to shortlist and find papers myself. For anybody new here, or if you just need a recap of the recap format, this is how it's going to go. We have 3 papers from journals and 2 from ArcSiv in the following order. The first one is a theoretical paper developing the mathematical and conceptual foundations, which may be elaborated upon in something like the second experimental paper, testing out all the conclusions, proving and disproving hypotheses, and providing some hopefully visually interesting physics in the process to later be used in the third applications paper, bridging the gap between physics and other fields like science, no, other fields of science like chemistry, medicine, and computer science. Maths doesn't count because it's boring and already within physics, okay? But you know what isn't boring? The fourth ArcSiv paper, which I consider to be in my niche. My niche being all the things related to particles and quantum mechanics, even things like quantum gravity, if I manage to find a paper on that. But of course, what's the point of science if we stay in our comfort zones, which is where the fifth ArcSiv paper comes in, one that's out of my niche but might be in yours, so stick around to the end. Now I have my usual disclaimers. I am not an expert, not a lawyer, nor a doctor, and I do not advise you play any drinking games associated with the sheer amount of filler words I use. Don't cite this video and don't do anything stupid. If you have corrections, feel free to leave them in the comments. We are all here to learn, and if I get my comments disabled, I'll have an email address in the description. But before we dive in, a special announcement. Spring has sprung and April is approaching. I will be doing a Twitch stream covering this year's ArcSiv joke papers on the 1st of April at 10 p.m. EDT, which may be the 2nd of April for you. It will be the 2nd of April for me. My Twitch will be linked in the description and is also shown on screen. Thank you so much, and I hope it will be fun for everyone. Also, it will be getting noticeably darker throughout the duration of this video because it is currently like 5:30. And also my voice is kind of dying, but we've all... So anyways, without further ado, paper 1, lava lamps. This paper, vaguely, if you squint your eyes really hard, talks about something similar to lava lamps. Specifically, it talks about what happens when gravity and heat flow counteract each other. This interaction results in something called a non-equilibrium steady state, which cannot be modeled by normal thermodynamics, and hence why this theory of global thermodynamics is developed. Although the setup in the paper is very simple, as you can see, a container with some liquid inside that is heated from like the bottom. A lot of cool things such as metastable states and potentially nonlinear dynamics arise naturally. By metastable states, I mean supercooled gas and superheated liquid. Although these may seem like they require incredibly specific conditions, they are just a necessary transition point as temperature differences cause gases to rise while gravity pulls the liquid that condenses at the top downwards, as in the setup in figure 2, right? You may also wonder, why might this transition be necessary? Can't the gas just go up, for example, on the left, while the liquid go down on the right, or some other less idealized case? And you would be stumbling on one of the potential problems, which is highlighted later in this paper in an example of the experimental setup, that being differences in temperature across the horizontal direction. Because this uniformity is challenging to obtain experimentally, the researchers propose analyzing the system numerically, something which they have already actually done themselves when analyzing another related system, the Potts model, which describes how spins in a ferromagnet can influence each other and the dynamics which come of this, including phenomena generally described as phase transitions. What was observed there is remarkably similar to this paper, except from what I can tell, there was nothing to play the role of like gravity, although I'm not familiar enough with the Potts model to say for certain. Perhaps a counteracting effect could be a magnetic field of some sort. In any case, I hope you're fascinated by my ability to go on tangents because I'm only now getting to the central theoretical result of this paper, which is a quantity called effective gravity, which encapsulates where the denser liquid goes. But first, I guess let's talk through the experimental setup. Yes, I am pulling up figure 1 here, and yes, this means we will have nothing to talk about in the next section. There is a container filled with a liquid. Gravity acts downwards, as gravity usually does, and there's a temperature gradient across the same direction along which gravity acts, so vertically. We denote the bottom temperature T1 and the top temperature T2. Yes, we are doing maths, and yes, this is going to drop my viewer attention rate probably. There is an upper portion and a lower portion, which state these are, and it is determined by the effective gravity. The effective gravity looks like this. Looks complicated, but all it's saying is there is some correction to the usual gravity, which depends on this uppercase omega parameter, which is the temperature difference, and it describes the heat flow. The other variables that appear are mass m and length or height of the container, most obviously. But there's also this V-bar thing, which is volume divided by number density, and it is the specific volume or inverse of density. There's a dependence on the derivative of the saturation pressure or pressure needed for a gas to turn into liquid at the average temperature across the whole container. Crucially, temperature is assumed to be linear across the vertical axis, which is what allows for things like consistency with other approaches and the existence of the metastable state to be proven perhaps just more easily. I'm not sure. In any case, I want to pause and think through what this equation is really saying, because everything in this equation is positive. Specific volume, like density, cannot be negative until we figure out negative mass, and speaking of that, mass also can't be negative. Neither can length, and a quick search in a database of your choice will show you that this slope of the vapor pressure or saturation pressure also is never negative. So really, all this equation is saying is if there is this upwards effect from being heated on the bottom, and if it can counteract gravity, then liquid will settle on the top, which is intuitive. However, by taking into account the saturation pressure slope, it encapsulates the effect of the overall temperature as well. If the whole system is hot, you best believe there's first going to be less liquid overall, but it's also going to be like pushed harder in a way, I guess. Also, as described in Appendix C, the form of this correction also means that where the liquid ends up settling does not depend on the height of the container. And let me find where this is. It is over here. Right, the form of the correction means it only depends on the temperature difference, right? Because the L's cancel out because, the volume is famously pi r squared times L. Only the radius ends up mattering, which makes it easier to verify the results of this paper experimentally. Although, as I said, this framework, this global thermodynamics, has shown good agreement with like normal thermodynamics when gravity is set to 0. Okay, going back. Oh, well, I don't think I can go in full depth into the maths, not only because we don't have time, but also because I don't understand it. I would like to point out the general approach. Like with any thermodynamics problem, the free energy was first taken and then minimized. A quantity psi is introduced to characterize the non-equilibriumness, or the deviation of the center of mass from the actual center times the number density. And what this quantity ends up depending on is what this quantity ends up like multiplying in equation 10 is going to be the effective gravity. There's some maths involved, but again, this is the thing that we end up minimizing. And from this minimization, we also get some conditions like temperature and chemical energy continuity, and this leads us to the metastable slash supercooled and superheated states. Okay. As you can see, further, we have like this minimization equations, and this is how we end up transforming this equation right here from the previous slide to depend on firstly this, and then there's some shenaniganry with the specific volumes that eventually gets us to the equation for effective gravity, because we didn't just pull it out from nowhere. And honestly, just read Appendix C, or B, sorry. I don't know the alphabet. Okay. Okay, so I'm adding this to the script later because I originally edited it out, but it turned out to have interesting connections later, so I'm also going to be talking about the Ising model really quickly. The Ising model, and more generally the Potts model, is a way to model interactions between individual electrons slash individual spins within a ferromagnet. This is done by placing them on a grid or a lattice in some way. As you can see, this lattice does not have to look much like a lattice. This is from an actual research paper that I will link if I don't forget. And the neat part about this is there's a lot of larger statistical behaviors that can be observed. Firstly, electromagnetism, of course, but also phase transition. And that's what these authors' other papers on the Potts model covered. This is stuff from their other paper. Interestingly, this isn't the only connection between thermo and electrodynamics, since one of the theories that the authors compare their work to, developed by Luttinger, I'm sorry if I'm mispronouncing that, also derives something similar to effective gravity, as highlighted over here, through mechanical principles based on a derivation in electromagnetism. Again, I'll link that paper below as well. Figure 1 is the setup. We talked about it. The only important part here is the selection of the reference point for which the gravitational potential energy is 0. Since we want a unique non-equilibrium steady state, this point is exactly in the middle. Note that this reference point is not the x theta noted here. That would be the interface between the gas and liquid position. Anyways, moving on. Figure 2 shows the dependence of the center of mass on the temperature gradient. In panel A, we see the graph itself, while in panel B, we see the physical interpretation of various regions on the graph. Specifically, since we assume liquid to be denser than gas, if the center of mass is high up, we will find the liquid to be at the top. An important feature of panel A is the sharp transition from liquid being on top to on the bottom when the temperature gradient is this value right here, and this obviously corresponds to the effective gravity going from negative to positive. Setting our old expression for GF to 0, we will be able to derive this. Mathematically, we will be able to derive this. Yes, thank you, script. I could have figured it out myself. And while this may seem complicated, note that this factor is this negative sign is just because, again, the liquid settles at the bottom. What have I written here? Yeah, okay. Hold on. I think I missed something on my slide. Wait a damn minute. First paper and we're already messing up. Woo! It's fine. Yeah, I forgot to add this equation on the slide, but anyways, yeah, this is the equation mathematically being graphed here. While it may seem complicated, note that this factor with like GF just gives us its sign, meaning if the liquid settles at the bottom, then the correction from the geometric center will be towards the bottom too, and vice versa. Admittedly, our big sigh here has been through a lot. While it can still be thought of as expressing how far the center of mass moves, it now also represents the fraction that is liquid at equilibrium. I think, specifically at zero gravity, not only because gravity doesn't affect the center of mass, but also because in the free energy equation, the one we're minimizing, this one right here, psi is used as a coefficient for the gravitational effects, right? So it does not itself depend on gravity. Now, the interesting thing in panel B is that, as noted by the paper, configurations 1 and 3 are spatial inversions. You can flip them around and they'll look like each other, well, minus that there's a bigger metastable portion in the third one than the first one, but right, the metastability is with the gas is supercooled. Configuration 2, on the other hand, has superheated liquid, and this configuration exists in this region where the bottom is being heated, but not enough to boil the water, which is what produces this effect of superheating. Meanwhile, in the cases of 1 and 3, the part that's being heated is where the gas is. And this configuration, as noted by the authors, warrants further investigation since it potentially includes things like nonlinear effects from what I can tell, but don't quote me on that, okay? Okay. Figure 3, panel A shows us how this gravity affects the free energy. It's pretty self-explanatory given what free energy is. The gravitation term is being subtracted because gravity is reducing the particle's free energies in some way. The gravitational potential energy is something that's being done on the system, which means it's not available for the system to use to do things like get to equilibrium. An equilibrium in which there are no metastable states, since I probably should have talked about this, but oh well, what characterizes a metastable state is that it only needs a small push or increase in energy in order to become a stable state. Or at least that is my incredibly oversimplified hypothesis, since this paper doesn't describe qualitatively what these metastable states are. Again, feel free to correct me in the comments. We are here to learn. See, what makes me doubt this explanation, even though I was the one who wrote it, is panel B of figure 3. Same figure. We're not going anywhere yet. For which we can see this line of constant effective gravity and these two states at the intersects. The first state is where there's gravity but no temperature gradient, right here, which is this very neat liquid-gas separation. Gas separation with no metastable states, and I presume there even is this phase separation because of saturation pressure, like the gas is pushing against the liquid, which is what makes it condense. I don't know, I could be wrong. Again, correct me. And the second state is where there is no gravity, but there is a temperature gradient, and there's actually a metastable state here with supercooled gas, which is interesting. Though I guess it does sort of make sense since the above argument with the particle's free energy needing a push depends only on this term, right? On the effective gravity term being in the overall free energy equation. And also, it would make sense given what we saw in the Potts model, right? As I said, there wasn't like a counteracting force in the way that gravity is a counteracting force here. There's also this figure in the appendix. I showed it before. It shows the critical radius, since again, due to the specific volume dependence of GF, the height of the container L cancels out, and the radius is what matters. I don't know, you can gawk at it for a while, I guess. Okay, done gawking. I don't really have anything for the further questions section. While a unification of two seemingly unrelated concepts is, of course, of intrinsic interest to me, and I'm sure the researchers, concrete applications evade me personally. That is not to say there are no applications. Statistical mechanics in itself is a very powerful framework for analyzing anything from biological systems, some of which we saw in previous recap paper 3, and medicine, to things like the society around us, which we will see in paper 5 today. Potentially even things like AI, paper 3, this recap. Stay around. This paper and this series of papers adds a whole new layer onto the framework, and the idea of two forces working against each other is, I think, general enough to warrant further study in this direction, which segues us into the next point, further directions of research. As I briefly mentioned, the paper does propose a pretty viable experimental setup. It appears that there is an experiment or experimental paper in progress by these authors since they cite their own results for like their whole point. In fact, um, ooh, I missed a whole line. They cite their own results for the claim of horizontal convection slash temperature differences being able to affect the metastable state slash like their whole point. In fact, temperature differences as small as 1 Kelvin. Okay? Which is like 1 Celsius. I don't know why I said Kelvin, but also there is another paper in the series that is presumably written but hasn't been published yet, which attempts to explain the second state in figure 2 with the superheated liquid. Also, I think it would be really fascinating to look at exactly what is happening at like this transition point of GF equals 0, perhaps numerically. My very uneducated guess is the whole thing becomes metastable, but we'll have to wait and see, I guess. All right, paper 2. This is the experimental paper, and it was very dense for me to read because of a quirk of the text where it constantly uses brackets. Like, it's genuinely worse than when I type, and anyone who knows me personally knows I go on so many tangents that a conversation with me might as well be a trigonometry class. In any case, it talks about some observations of galactic cosmic rays, GCRs, done by the Khaled Observatory on the International Space Station. Yes, there's observatories on the International Space Station. I find that awesome. Like, that's so cool. Please listen to just how cool this is. Anyways, specifically, it analyzes some data from Khaled and another older detector to make a model explaining how the sun affects what we observe. It appears to be a well-known fact in solar physics that solar activity varies with a period of about 11 years. With this come variations in the sun's magnetic field, things like sunspots, which are discussed, but also the polarity of the sun's magnetic field reversing, which is crucial. Yeah, this is the sun's magnetic field will flip soon thing you may have heard last year. While the polarity reversals are in fact a thing that happen, from what I've read, the story is a bit more complicated since the sun doesn't act as a dipole or what you may think of as like a magnet with a north and south pole. Instead, since the processes that cause the sun's overall magnetism are also the ones that cause sunspots, which have their own magnetic field lines, like yeah. So in so basically these processes cause the sun's sunspots and the solar maximum, which is where the sun's magnetic field flips. There are so many sunspots that it's hard to define like a north and a south for the sun. In the paper, the relevant concept of like overall magnetism is the heliospheric current sheet, HCS, which is like this rose-like surface that represents the sun's magnetic current. I'm gonna try to find the image again, actually. Yeah, it's like this thing. Yeah, it's this like rose-like surface that represents the sun's magnetic current as it is felt throughout the solar system. The reason this is important for the paper is that, of course, electrons and protons in the life would interact differently with this sheet due to their charge and also depending on the polarity. In the paper, this is defined as QA less than 0 and QA greater than 0. Q is charge and A is polarity. And from there, the paper provides a qualitative analysis of time lag between the sun's magnetic activity and how many electron and proton observations are made and how long it takes a change in the magnetic activity to affect these observations. A main result of this paper is that there's a significantly larger time lag for electrons than protons in the positive polarity epoch, for which the electrons are the ones more like affected by the current sheet in terms of drift, whereas the protons are more repelled by the sheet and hence drift less, primarily reaching Earth through a trajectory through the poles, right? The exact argument in the paper is reversed with electrons going through the poles, but I wanted to keep consistent with the epoch. So don't get confused if you decide to read it yourself. The reason the argument can be reversed is that this paper shows that upon a polarity reversal, all I just talked about gets flipped. Protons have a longer time lag compared to electrons. So, as has become practically tradition, and also because I need to justify this as the experimental paper, I want to talk a bit about the CALIT detector and the other detector whose data was used, that being the AMSO2 detector. We will get to it. So, CALIT stands for Calorimetric Electron Telescope, and its purpose is to observe high-energy astrophysical phenomena such as particles from supernovae or black holes, and also things like searching for dark matter. The schematic for CALIT is shown on screen, specifically the calorimeter. It's right. The first CHD, don't pronounce it chud, don't pronounce it chud, or charge detector does exactly that. It detects the absolute, so I presume total, charge of the incident particle shower, basically a lot of particles. This is done using scintillator paddles. The atoms within these get excited by the incident particles and emit photons as they de-excite. The energies of these photons are then analyzed to determine the charge. Due to the existence of positrons and antiprotons, however, this is not yet enough to tell the electrons and protons apart, although we will see that the positron versus proton distinction does not matter much for this paper later. Yeah. So next is the IMC, or the imaging calorimeter, which figures out the trajectory of the particles through the detector along with the incident direction. It also provides its own charge measurements for individual areas in the particle shower, and for that, I think it has scintillator fibers, not paddles. It also has tungsten. I'm saying that purely to add a tungsten cube to the thumbnail because I need this thumbnail to be clickable. Finally is the total absorption calorimeter, or TASC, spelled with a C because they want it to be so extra, and it is used to measure total energy, hence why it needs total absorption, and it is also used to tell electrons and hadrons, so protons, apart. It has like tungsten logs, as they're called, and due to their crisscross arrangement, they allow us to get the center of the incident shower. CALIT's whole thing is that it can detect very high energy particles, and having many layers of these logs is what allows for this. I'm not 100% sure this explanation is correct, but from what I've been able to gauge, how much energy is measured is directly related to how much energy is lost. And if not all energy is absorbed, then that means we cannot get an accurate measurement. The crucial part is then like this line in the development paper. X0 is the radiation length, or the length it takes for a particle's energy to be reduced by 1 over Euler's number. I'm not going to try to say Euler's number because I do not remember Euler's number by heart. Unfortunately, I'm such a poser. The value of 31 radiation lengths, or 30 radiation lengths, cited means even a particle at 100 tera-electron volts, the highest energy mentioned in the paper, would be reduced to just over 3 electron volts. No prefix, no nothing. 3 electron volts. The other detector, AMSO2, is used to verify the paper's hypothesis that there is a time lag asymmetry between even and odd solar cycles. This is the phenomenon shown in panel D of figure 3, if I manage to scroll to it correctly. This is panel D of figure 3, where the maximum... No, it's not. I'm wrong. This is panel D of figure 3. I'm right. Where the maximum time lag comes earlier for the type of charge that has a longer time lag. Right? Go over here. It's getting longer. It's getting higher, so this area is getting longer. Anyways, the AMS detector's main scientific objectives were to detect events related to antimatter and dark matter. The relevant detections are for positrons and antiprotons, although, of course, to detect these, AMSO2 must also capture electrons and protons, and this data is precisely what is used by our paper. Well, it's not our paper, the paper we're discussing, which I abbreviate to our paper, or OP. Also, I want to clarify a few definitions, or just like one definition. COR, or cutoff rigidity, is the last rigidity for which a particle does not fall back to the source of some magnetic field that it is in. Rigidity itself is how much a particle resists being deflected by a magnetic field, defined as its momentum divided by its charge, right? Intuitively, if a particle has a large momentum, it plows through the magnetic field, kind of like an escape velocity for the Earth's atmosphere, for the Earth's gravity. Well, if it has a small charge, it can't really be affected. It's like trying to pick up plastic with a magnet. That's it for now. Any other definitions which need to be introduced will be introduced over the course of explaining the figures. And speaking of the figures, figure 1, panel A, plunges us immediately into the deep end by really being the most important one. In panel A, we see the raw data of the detected number of protons and electrons against the year it was detected, right? This graphs. And here we also see the older data from AMS, which is what we talked about, right? In gray is the number of sunspots observed. In late 2019, early 2020, comes a bit earlier than the, like this minimum of sunspots comes a bit earlier than this maximum of protons and electrons observed in like mid to late 2020. We also see that the red graph for protons is more smoothed out, whereas the graph for electrons has much more pronounced peaks and valleys, and this isn't actually due to anything like mass, since again, protons and positrons, all positively charged particles, are treated the same by the analysis. Hence, this is another solar cycle dependent effect. If we were in an odd solar cycle, then the positively charged peaks would be more pronounced instead. Panels B and C, on the other hand, are confusing. They show the cross-correlation coefficient between time and time lag for both electrons and positrons graphed against the time lag itself. What I think these are showing is how likely it is that at a certain time, in this case, in the case of panel B, this is at Carrington rotation 2230. Carrington rotation is a rotation of the sun about its own axis, so kind of like how days work on Earth. Yeah, and what I think this is showing is the possible or most likely value for the time lag. So, and the closer this gets to -1, this cross-correlation coefficient gets to -1, the more Likely it is that this is in fact the time lag that is happening at a particular time, right? In the case of figure C, this is a different Carrington rotation. Because cross correlation is basically a measure of displacement. So, like I said, in panel B, these values are incredibly similar, quoted as 11 for solar, quoted as 11 for electrons. Is it? No, quoted as 11 for protons and quoted as 12 for electrons. And the cross correlation for protons is likely closer to -1 because the shapes of the proton graph in panel A of the same figure is more similar to the sunspot number graph, right? Right here, it's more like smoothed out, just like the sunspot number graph is. And you can roughly confirm that by looking at panel A and knowing that the length of a Carrington rotation is about 27 days. Somewhere around the center of this peak is panel B. This peak is around mid-2020, while the low of the sunspot number is around late 2019. Something completely different is right, like so this is around 11 months. Like if we say that this maybe is June, and I can't do math right now, but yeah, this is also like around mid 2020, mid to late 2019. Anyways, something completely different is visible in panel C. However, um, yeah, it's around April, May of 2016. So this region right here, where the proton graph is quite higher but has the same overall shape as the electron graphs, hence the stark difference in the cross correlation coefficient and time lag itself. Though really this whole gap was just to justify to myself that I'm interpreting this right. Again, feel free to correct and or eat me in the comments. Figure 2, on the other hand, is a complete breeze. It's simply here to confirm that we can, in fact, use AMS data, since the specific methodologies for collecting and interpreting data are a bit different between the two data sets. However, by showing a nearly one-to-one correlation between the AMS and CALID data for the period they were both in operation, which is this right here, so from like 2016 to, let's see, like 2019, like early 2019, I would say. Um, yeah, figure 2 confirms that we can use AMS's findings from the odd solar cycle that CALID doesn't cover, and it can be used to prove the points stated by CALID. Panel A shows the correlation for positively charged particles, while panel B for negatively charged particles. And the correlation is the slope. And those points that CALID is stating are shown in figure 3. Panel A shows the GCR flux, equivalently proton/positron and electron counts, as well as sunspot number graphed against time. We have in fact played these games before in the A over 0, so positive polarity half, and okay, to clarify, because I got confused about this when I was researching, A over 0 is for this whole like thing. It starts after this, what looks like a solar minimum, but is actually a solar maximum because this was inverted to make it a bit easier to read, right? To see this, well, cross correlation better, right? The time lag better. So A over 0 is for this entire right half. A less than 0 is for this entire left half. And in this A over 0 half, we see that positively charged particles have an overall smoother graph than the negatively charged ones, although magnitude is not taken into account here. In a less than zero, on the other hand, we see the exact opposite of this. And this is the central result of the paper. Panels B and C, right here, are another way of showing this with flux graphed against sunspot number. And crucially, these are cyclic with sunspot number. Panel B shows the cycle for this a greater than zero epoch, but and you can verify yourself that these values check out by starting like at the polarity reversal just after this max label and going to the end of panel A right here to like the next solar maximum without capturing like without capturing the without like wrapping back around to this end. Yeah. Again, it looks like a solar minimum. It's actually a solar maximum. Panel C makes a point to capture polarity reversal instead and goes for the duration of the entire even solar cycle, right, which contains this polarity reversal within it. Now this is what gives these unique distinct shapes, right? This is the transition. No, B is the transition between even and odd solar cycles, and C is just the even solar cycle. And lastly, we have panel D, which basically does what figure 1 panels B and C did with calculating time lag and plots that for the whole duration of the study. Note, if you're going to go about cross-referencing this with figure 1 panel A, that the current panel is graphed against solar rotations, not years. The result with 11 and 12 months for lag for positive and negative charge respectively can be observed around this 200 mark, right? Just before it becomes, just before the lines start coinciding. All right, on to the further questions. What does this change? AKA an excuse for me to yap about applications. Frankly, I'm not sure what kind of applications can be drawn from this paper because I do not have a background in solar physics. I don't. I'm high school aged. How would I have a background in solar physics? That being said, there were already models used to calculate the rigidity of incident particles. In fact, you can like look it up. There's online calculators for it if you want. For incident particles and their trajectories around the HCS, heliospheric current sheet. So I doubt that like a reverse model where we predict the sun's activity through CALIT measurements would be useful. The main thing I've been able to glean is a potential like meta application, that being to more accurately predict the original source of incident particles by taking into account the effect of the sun's magnetic field on their path, right? Like being able to calculate where, when, how astronomical astrophysical phenomena come from using data like from this experiment using the time lag data. Further directions of research, although this paper has basically proven that there is this charge-dependent time lag and provided a good explanation in terms of the drift model originally developed in reference 8, which is another paper by the same authors, by the same collaboration. It did so mostly qualitatively. It is noted by the paper that while the heliospheric current sheet, which causes the drift effect, is the main source of the time lag, there are still other factors like solar wind, which is like relatively high energy in the low keV range, kilo electron volts range, particles coming from the sun, which need to be accounted for. The paper also mentions turbulence, presumably in this solar wind, and something I think deserves a mention is that the field which studies the heliospheric current sheet is called magnetohydrodynamics, which I think there's like this really neat overlap in the terminology between that field I'm not going to pronounce again and fluid dynamics. Anyways, these factors need to be considered in order to have a more robust quantitative theory of the drift effect, which is something I assume the authors slash the collaboration are working on. It has only now occurred to me I should probably be reading the names of these papers out loud for anybody that can't see or is listening to this. Okay, so the third paper, an efficient deep reinforcement method for smart particle navigation in complex flows by Xuanlu et al. Um, yeah, this paper is kind of boring. So I don't know, just like split screen subway surface footage if you want. I don't really know. But yeah, this paper is about a new reinforcement learning technique developed throughout this paper and how it compares to the other approaches taken earlier. This new technique is called ENCRDQN, or Exploration Network with Clustered Experience Replay Deep Q Network. Basically, it takes what you typically would think of as reinforcement learning, right? Rewarding the algorithm when it does something good and punishing it when it does something bad, and adds two crucial things: continuous variables and clustering. To understand the first part with continuous variables, we must note that typically reinforcement learning only allows our agent a discrete set of actions it can take. And as the paper notes, this is fine for spaces which are either discrete themselves. Think, for example, walking on a grid, or I don't know, something like the icing model. That just came to mind. Probably not relevant, or can easily be discretized, where any data loss or error caused by discretization, right? Turning continuous data discrete is negligible. Unfortunately, this is not the case for the use case of ENCRDQN, that being medicine. You really have to be precise if you're going to be doing things like drug delivery, for example. And this continuousness is achieved using interpolation, where the model can select the best action given the continuous parameters, and then an allowed discrete action is chosen based on what the network wants to do. While this may seem pointless since the action space doesn't change, it makes the network more robust, as we will see. Clustering is the grouping of past training experiences based on what happened, and it not only ensures representativeness of the training data, but it also improves our ability to understand what the network is doing and why it is doing something, or as I like to call it, debuggability. So then you may be asking why this paper is physics, and this is a good question for every applications paper. That's because the authors ran an excruciating number of tests on these models where the agents slash particles, as they're called, navigate through various fluids. Specifically, they tested how they adapt to and use their environments to achieve the test's goal more efficiently, consistently, etc. Cool. But first, the other models. Our ENCR-DQN is up against a few other modified DQN approaches, as well as like a standard deep Q network. It'd probably be helpful to know what a deep Q network is, as well as the thing it's based off of, Q-learning. Q-learning is a way to get agents to do specific tasks with reinforcement learning, which means they get rewarded when they do something correctly, and their overall goal is to maximize the total reward function, which is this Q function right here. While this is all fine and dandy, and you may even know how to maximize a function, it is not so simple when this function isn't an algebraic one, but instead a series of actions that our agent can take. Specifically, this series of actions and consequences is tied together into a Markov process or chain. I swear, we're 2 for 2 on Casane-Teto references in our applications papers. We're 2 for 2. I think this says something about physics. Physics likes Kasane Teto. Anyways, I'm referencing Machine Love by Jamie Page. Because every step or action must necessarily lead somewhere, and this is like the basic premise of a Markov chain, right? And it leads to a new state, which the agent must adapt to and hence a new action that the agent takes. The agent maximizes their reward by developing a policy, a set of rules that it follows, which depend only on the state of its environment. I will actually show you some policies that ended up being developed. This is a policy, for example. These are the directions in which our agent moves in depending on the orientation and the vorticity. Again, we will get to this, but this is like what the um, policy space, you can think of it as something similar to phase space, looks like. Right, and so policies are a set of rules it follows, which depend only on the state of its environment. Something like this. Q-learning and deep Q-learning. This policy is characterized by some probability that the agent takes a specific action in a specific scenario. And if you know about a bit about machine learning already, you may be thinking, hey, that sounds something like something a neural network would spit out, and you would be exactly right. The DQN approach and all its derivatives in OP, our original paper, are based on a neural network, as seen here, and also as seen here, this Q network right here. And this is also a figure in the paper itself. We'll get to it. Aside from the standard DQN, there are three modified approaches employed here. First is prioritized experience replay, or PERDQN. I might be saying per DQN, just forgive me. I like cats, I guess. Experience replay in itself is a technique which lets the agent learn from past experiences as well as what it sees in front of its face. Past experiences are given to the agent while it is also gaining new experiences and learning based off those, and this technique improves results when real data is hard to come by, or if the error part of the trial and error of reinforcement learning would have major consequences. Not gonna lie, I thought experience replay would be like fancier when I was researching this, but no, it's really just feeding the learning algorithm the same data over and over. Prioritized experience replay is marginally fancier though, since instead of choosing experiences to replay at random, it chooses experiences that like are rarer in whatever way and that have the potential to affect the model's training the most. Again, because of limited data is where experience replay excels most. And this is the paper, the one singular paper that I could find on prioritized experience replay that like actually explains the premise. But anyways, another version of DQN is intrinsic curiosity module, or ICM-DQN. This approach, instead of relying on feedback solely from the environment, gives the agent its own reward function, which is based on how much the agent may learn or how unpredictable of an experience it may have if it takes a particular action. This is helpful, for example, in terrain where there is no clear goal, or tasks in which there might not be an extrinsic reward from the environment every step of the way. For example, ICM-DQN is what allows an agent to learn to play Mario Bros. Without an extrinsic reward. It just wants to play Mario Bros, which is honestly kind of a mood. Like, I would rather be playing Mario Bros than recording this right now, but hey, I'm doing this for extracurriculars. We ball. We always ball. Anyways, this is helpful. Oh, no, I already said that. This approach is also helpful for agents which need to have a diverse skill set, since the agent will learn things even if they do not correspond directly to any particular goal. Lastly, we have NoisyNet, whose premise is just to add some random noise to the model's inputs while it is training in a way that enhances the environment rather than just being noise that the model must learn to filter out. An interesting thing about this is that the original noisy net paper draws parallels with the intrinsic curiosity approach in that whoever's training the models is changing things manually about its training, but where ICM has some predetermined intrinsic reward function that might mess with training, the noise of NoisyNet is Gaussian random. That being said, as OP highlights, whether or not this noise is actually helpful might be debatable, since apparently it's reduced quite quickly in training from what I can tell. We are going to talk about the two modifications that make ENCR ENCR in the next section. Now, there are a lot of figures in this paper, primarily from the many tests the agents were up against, which is why I won't be talking about every single one of the figures like I usually do. One of the details of exactly by how much ENCRDQN outperforms the other models will be omitted because nobody wants to listen to me list numbers all day, unless you do, in which case leave a comment and I'll do that over on Twitch. The things I do for the bit. But the fact that it does will be obvious from the figures I do show, right? The fact that it does outperform. So without further ado, figure 2 is a diagram of what happens every training step or episode. Let's start with panel B, since panel A only adds to this architecture. At the center, we have the agent, our DQN. This Q neural network being at the basis of it. The Q network can give two possible actions: to explore and gain new experiences, or to exploit, doing what it already knows will give it a higher reward. The network is designed in such a way that it usually, with probability 1 minus epsilon with epsilon small, chooses to exploit, because again, it wants that reward. The action is then further chosen to have the maximum reward in both cases. This action is fed into a loss function, which determines how far off it was from theoretically optimal. How that is calculated is completely and utterly beyond me, but it is. I'm gonna pause the video to go turn on the lights. The lights are on and we are back in business, baby. There's also this experience replay module, which basically adds another step to training, again, reusing old data like we said before. After all of this happens, the action is actually done, and the agent receives a new state from its environment, as well as the reward. It's important to note, except in the case of ICM, this reward comes directly from the environment. In the real world, what is considered rewarding must be picked so that we get the agents to do what we want. In the tests, however, we can control exactly what reward the agents get where. The two key changes to the setup in panel A are how exploration is handled and clustering of experiences from replay. From what I can tell, exploration and exploitation are now on equal footing, with neither being favored. Could be wrong. It could still be using that epsilon and 1 minus epsilon thing. Yeah, this makes the first modification not complete overkill, considering it introduces a whole different neural network. Yeah, oh, I can zoom in PowerPoint. That's awesome. I did not know that. This is horribly grainy. Okay, never mind. We are not zooming in. Yeah, so it like introduces this neural network, which guesses what happens in between all the possible actions that the agent can actually take and selects from there. Note the process is still random by virtue of how exactly it interpolates and finds this in between, that being with the functions shown in figure 1, the beta distributions. I will not be showing the beta distributions because they are boring, and also I want you to read the paper yourself since I'm not going through this alone. Overall, you can think of this modification as if the agent wants to go to the top left and to the top right, then we can even that out and go to the top instead. The second is experience clustering. The paper justified doing this with diversity, equity, and inclusion, y'all. I'm a DEI hire at my job. so that the model doesn't get stuck being fed experiences of all the same type over and over again, which can lead to overfitting, aka the model adapting too much to specific scenarios. We will see this. We will see this and it will be funny. Yeah, so clustering and replaying experiences from different clusters each time means the agent will get a more representative set of data. Also, this little swirly inset is never explained in the paper. Sorry, I think it looks pretty cool. It might be related to how the environment rewards the agent, I guess. I genuinely don't know. But anyways, we finally know what ENCRDQN is. Awesome. Time to throw it at a bunch of tests. First, going upwards. Seems simple, doesn't it? Yeah, figure 3 shows the environment they're up against, a fluid that's spinning around. Seems simple, doesn't it? They will fail comedically. I promise you, they will fail comedically. Oh my gosh, I laughed so hard when I was reading this paper. Their goal is to get as high up as possible within a limited number of steps. The dot in the middle here at 0, 0 is where all the agents start, and their tasks is to use the fluid's vorticity in their favor to move upwards. Figure 4 shows the reward curves. Shows how much how much all the models are like learning. Not every step of the way, and also by the end of the training at 800 episodes. Okay. Yeah. You can see that there is some dips toward the end, and this is kind of to be expected due to overfitting. As we can see, exactly what the agents were doing in figure 5, which shows their paths in the fluid. Also, the naive approach is basically like ignore the fluid completely, just going up or just like choosing the up action, not even seeing where the fluid takes it. Yeah. DQN and ICM have the wildest paths, getting quite far up to the sides. And this makes sense for ICM since it's inclined to try a lot of things. NoisyNet, on the other hand, had a very similar paths almost every time, though it did go downwards more than every other model except Naive. PER and ENCR look very similar, PER just having a bit more variability, and ENCR getting to its highest of 9 pi more overall. Right? The highest is like the same at 9 pi for both PER and ENCR, but ENCR gets there more consistently. Figure 8 is interesting. I showed it already. It shows what the models choose to do based on where they are, so particle orientation and vorticity. ENCR has the cleanest figure with well-defined regions and no major like patchy spots where slight change can cause a completely different decision. For example, like with PERDQN, we see that in this gray region that chooses to go southwest, there is this spike that chooses to go up. We don't have anything like that in the ENCR DQN policy, except for this tiny, tiny dot. I don't think you can even see it on the recording where it chooses to go right. But again, that's really negligible. I think it might just be like the start of overfitting. I don't know. The second test is largely the same, going upwards but in 3D. I will leave figure 11 up on the screen for a bit since I find it incredibly funny. I mean, what is PRDQN doing? It's going sideways, apparently. This might be because like the prioritization got stuck prioritizing experiences that made it go sideways, but it's hilarious nonetheless. Like, is it even trying? NoisyNet, as well, just failing to go upwards. Just failing to go upwards. These squares are where they start. No, these, oh no, wait, these squares are where they end up. Yeah, the squares are where they end up, but still, like noisy net is just a tangle. Like, what are we doing? Um, yeah, ENCR though, you gotta give it some credit. It just showed up and it worked. First try. Showed up, started going upwards. Awesome. Peak. Cool. Um, like, and obviously the naive approach failing miserably, but what do you expect? ICM doing relatively well, I would say. Like there's this offshoot that goes sideways. DQN on par with NoisyNet, I would say, but did not reach the like same. Did it reach the same height? Okay, like maximum height it reached like 50, but the maximum, yeah, actually the maximum height NoisyNet reaches also like around 50. Okay. Anyways, the last experiment that the authors did was something really similar to the slime mold demos you might have seen. And it's target navigation. The agents would be given a huge reward if they get all the way across this board right here, with smaller rewards the closer they get, and they are killed if they hit the edges. Seems harsh, but okay, you gotta make them learn somehow. And I accidentally closed my script. Hold on. Also, there's some Brownian noise going on in the whole board, which the agents must adapt to. In figure 15, we see the approaches did about as well as each other, learning pretty quickly where to go. Except NoisyNet. I have no clue what NoisyNet is doing. It appears to have invented a goalpost slightly above the first one, and it's going there instead and getting killed. And ICM had a couple offshoots, but I guess that's like predictable to some extent, and also like it learned pretty quickly. Like it really did learn pretty quickly. This, yeah, like it's like it's fine as seen here. It's not even like the lowest. PR would be the lowest. Anyways, yeah. Though interestingly, like Ian's here also had this huge offshoot, which I don't know where that came from, like at all. Yeah, also just how poorly NoisyNet did is evident in this panel B of figure 16. Like it's a good 30. It's a good 30 reward points below everything else. Like it's trying. You gotta give it credit. It's trying. It's failing though. Um, yeah. Another type of test the authors did is an ablation test, basically to confirm they didn't add something pointless to the ENCR approach. They confirmed the full ENCR agent against two gutted versions, including only one of the two modules, Exploration Net DQN and Clustering DQN, as well as Standard DQN. Using these same tests above, 2D and 3D going upwards and target navigation. So like for the going upwards task, full ENCR outperformed the gutted versions for almost everything. Let me see if I added. Yeah, okay, yeah, I did add it. Exploration Net did, however, no, it wasn't Exploration Net, it was Cluster Net. Managed to. Wait a minute. Wait a damn minute. Oh, I lied. This is irrelevant. Never mind. Yeah, they performed about as well as each other, except for Cluster DQN, which had the highest average length, though I'm not sure if that's a good thing. Question mark. In any case, the target navigation hit ENCR DQN much harder, with it only beating out its competition in the test phase. That being said, the authors do stress that the test phase is the most important one. That being said, given PER's generational fall off between the 2D and 3D upwards motion task, one may say that choosing the right approach for a specific problem is important. Despite winning in some train metrics like training success, right here, it Did um Oh no, over here. Despite winning some metrics like training success, exploration net struggles a lot with staying consistent. Hence, the confidence intervals taking up the entire graph in panel B of figure 22, taking up most of it in panel A, with the reward curves for the full training process, whereas B is just the last 300 episodes. And it reminded me of this meme, so I put it there. It's my video. I can do whatever I want. Phew. All right, what a doozy. Further questions. What does this change? Not gonna lie, I thought there would be like more stuff in this paper when I first selected it. Like, okay, the abstract mentioned soft matter, which is partially the topic of the previous edition's applications paper. Wink, 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 wink. I can't talk today. Wink, wink, nudge, nudge, but it didn't go into any depth about that, like at all. In any case, soft matter slash robotics and soft matter robotics is still definitely one of the applications. The target navigation with the nav no, not the target navigation, the normal navigation tasks with the vorticity correspond roughly to navigation in blood, and the target navigation task is to test for precise delivery of medications for example, treating cancer. That's pretty cool. We don't want cancer. No, we don't. And also things like precision surgery mentioned again in the abstracts. Okay, awesome. Further directions of research. Oops, sorry about that. The thing pointed out in the conclusion regarding next steps is scalability. While ENCRDQN may be a viable approach for the specific, like idealized scenarios shown in this paper, doing something like what DeepMind researchers did with training a single DQN to play several Atari games a while back, right, making sure the advantage can be generalized is challenging. It's challenging because of how much computational power is required for training the ENCRDQN agent, which is something we saw when the full agent did not outperform its gutted counterparts, right? It might have just needed some more training steps, which is like it's still is it competitive? No, it's not really competitive. Never mind. I don't know why I said that. Um, in all seriousness, it does beat out DQN in a lot of places. Yeah. And in general, choosing an approach for a specific task is a task in its own. Further down the line, researchers would have to consider this computational overhead if there are constraints such as optimistically in clinical trials. On the bright side, though, the researchers have stated optimizations can be made. So again, we'll just have to wait and see what the researchers come up with later. I would like to preface this paper, Quantum Computing with Anions is Fault-Tolerant by Anasuya Leons and Benjamin J. Brown, by stating, please never let me live down the time I confused anions with axions in the previous recap. I need to be bullied a little bit. It's for character development. Anyways, this paper is about error correction and detection. Probably the other way around, error detection and correction, actually, in quantum computing. As you may know, getting qubits or quantum bits in quantum computers to not lose their superposition is incredibly hard, requiring precise conditions, and even then, error correction is a major issue. This paper proposes a way to solve that using anions, which are quasi-particles that exist only in 2D space. Then, by measuring these anions, which I can assume we can do because they're quasi-particles and this measurement doesn't lose the superposition. And if we see an error that persists with another measurement, then that means there's a physical error that needs to be corrected. However, if the error doesn't persist, that means it's a measurement error and only the measurement device needs to be recalibrated slash the erroneous measurement needs to be discarded. Note that I'm oversimplifying. In actuality, this algorithm also takes into account how like far apart the errors are, and this is due to causality. If two errors that are some distance apart are detected by a detector some distance away, then the algorithm only commits to correcting the error once it can be sure that it hasn't made two separate measurement errors, aka when the errors have persisted long enough that we can be sure that they are related to each other. To give a slightly comedic analogy, okay, actually a very comedic analogy because I'm funny. It's like a website forcing you to literally wait 18 years before you can confirm you're 18 years old. Although I do think this is only half the story, since it's impossible to properly correct errors until all erroneous anions are found. Errors are corrected by first ungauging, a process that, from what I can tell, transforms anions in a way that we can more easily work with them. It's complicated and mathy though, so I'm not sure. Feel free to correct me. Then the erroneous anions are annihilated, and this is what required all anions to have been detected, and then re-gauging is performed, and it was proven in Appendix C that this whole process does not affect the computation overall. Not only that, but because annihilating erroneous anions that just appeared can prevent, but also reveal further errors with the computational anions slash ones deliberately created, it's incredibly important that these anions are caught in time by this rule set of the decoder of correcting as soon as we're sure there is a real error. And it's also proven that this approach does not have too much time overhead, that waiting for confirmation is a problem. Because, right, the concern would be the error spreading, such as in figure 2, but with sufficiently low error rate, this is achievable, and this decoder results in fault-tolerant quantum computing. Awesome. So, anions. Glaring thing you might know about anions is that they're 2D particles. You might think they're not very helpful then, but given the right material, this 2D space can be replicated in our 3D world. Think something like atom-thick sheets of graphene, but really it's called topological materials. Anions, by their very nature, store information about what kinds of errors might have occurred to them, which means measurement errors that do not need intervention and actual errors that do need to be distinguished. And this is exactly what the paper proposes. See, unlike bosons and fermions, whose wave functions don't particularly care where you put them and how you switch them around, anions retain some memory of their previous states relative to other anions, and I'm actually not sure how this relates to entanglement, i.e. if the memory is tied to a specific anion. I think it is. I'm not sure. You might have seen this illustration when it comes to anions. I swear, don't take a shot every time I say anion. I cannot pay for your medical bills. Don't do that. Right? And in 3 dimensions, it's possible to loop around a particle without snagging on it by virtue of moving it upwards. And this is not the case for anions. And this snagging is at the core of the phenomenon of braiding, shown here. Since remember, particles aren't rigid spheres and are instead defined by a wave function, and this wave function gets changed in a way that a fermionic or bosonic one doesn't. This means that by braiding anions together or interlocking these loops, right, interlocking these space-time loops, question mark, we can get the anions to store some information and perform computation. This is where the icing model comes in handy. The paper I read, which will be linked about anion computation using braiding, uses the icing model to, well, model so-called icing anions that follow a certain set of rules when interacting slash braiding together. And also when fusing together. If you know anything about the fractional quantum Hall effect, this follows the same principle. assuming I'm understanding both effects correctly. When one anion loops around another, their wave functions, so where they might be, change by a fractional amount depending on the type of anion. Because yes, there are types, we will get to it. There's like electric and magnetic anions, and also like some pseudo-magnetic, pseudo-electric anions. Again, don't quote me on that. That is like the one part of this paper that I could not wrap my head around. Anyways, speaking of error correction, even though we were not speaking of it at all, how errors were detected is quite important, and I want to talk through it again. And this is, from what I can tell, conventional. Some so-called stabilizers that measure whether or not a particle is at a certain point in the lattice. Remember, Ising model stuff is on a lattice. Turns out that these stabilizers don't actually measure any properties that would cause wave function collapse, just binary true or false. In any case, these stabilizers themselves cannot be trusted. They are prone to error, which is why we need to build so-called detectors, as seen in this excerpt from the paper, that compare the previous measurement to the current one. This is the string thing. We will get to the string thing. If two detectors comparing two stabilizers both return that there is an error, that's something worth investigating. However, we cannot act on it immediately because the problems with messing up a computation are greater than ignoring it for like a few more steps. This is why if instead the detector notices that like the error goes away after the initial measurement, it's considered a measurement error. If on the other hand it doesn't after some period of time, formalized in figure 9, we commit to correcting the error using the ungauging regauging process I mentioned. And this is all done in a fraction of a second by the so-called just-in-time decoder. If you're a computer science student, you're entitled to compensation if you actively recoiled at having to hear that terminology again. Okay? Okay. Also, this is an excerpt from Wikipedia. It's Wikipedia's 25th birthday, or 25th birth year. It's turning 25 this year. I think we should acknowledge that. It's definitely going to be like at the year-end physics draft, but I just wanted to point that out. Here, I might make a separate video on it sooner than when the year ends. So anyways, figures. Figure 1 shows many things. First, it shows the braided anions, and they do look braided along the time axis, which is them looking crisscrossed. These anions are prepared using gauging. At the bottom here is an indigo ungauged regions where all the errors mostly occur in the gauged transparent region, right? They do not occur here because we're not even doing anything down there. Let's see. And these errors are represented by the red squiggly lines, with the one on the left being deferred to the present and the one on the right being corrected in the past. By once again engaging this small region around it, which is something we can do because of the large separation between the anions, and then regauging in the present. Really, this error that has been corrected is two errors, once again referring to figure 9. Do I not show figure 9? Oh, I don't show figure 9. I should show figure 9. Hold on. I'm like microdosing, giving y'all the live stream experience. Like y'all are watching me figure this out in real time, just with how I pause and unpause. Anyways, this is figure 9 for you. Um, it's pretty cool. Yeah, it talks about like how long we have to wait for the errors to be corrected. Ignore there's text behind this, and yeah. So we see that the reason the error string on figure 1 looks like it has some difference in time isn't because of a measurement error, although I would be curious to learn how this decoder deals with compounded measurement and physical errors, but rather because each anion in this pair that will be annihilated, forming the error string was detected at different times, right here. Like this. No, more so like panel A of figure 9. Yeah, okay. And this illustrates the deferring mechanism. It can't do anything until it finds the second anion, which the first one needs to be annihilated with. It might perhaps clue you in if you're confused on what engaging is, to know that logical readout, so getting a result from this computation, is also done by engaging. Basically, it's getting it into a form that we can understand and manipulate. Figure, figure 2, panel A, shows what is needed to produce a logical error in the computation, one which this paper does not propose a way to come back from, but I presume, like, since it's caught early enough, it will not occur. Presumably. And what is needed for this is an excitation, an erroneous anion, to propagate from one end of the braid to another, so from one anion to another. Because the anions are sufficiently separated, this will not be a problem unless we don't catch the error in time, right? Which is what happens in panel B. Also, this distance D has to be like greater than this this distance shown like here. Like 5q to the n plus 2q is arbitrary. I feel like I've written a section on that. Yeah, I have written a section on that. But yeah, sufficiently separated just means like it has enough time to catch the error before before it moves to another anion. Anyways, yeah. Panel B shows what happens when we do not catch this error in time, and this error has propagated to the next like rung of this braid, and this may continue until the panel A scenario occurs. Annihilating these anions early can also reveal other like syndrome or error information that the scenario in panel B hides due to the error propagating out to the next rung or next measurement. In panel C, annihilating the initial gray erroneous anions reveals these red ones, which are then corrected further. Okay. Figure 3 shows the setup used in fusing or annihilating erroneous anions. There is something of a conservation law that needs to be understood for this part. And um, that if there is like some region with a computational anion, no matter what errors occur, after fusing all the anions together, you will get the original computational anion back. However, to check that we do in fact have all the anions, we ungauge as in panel A of figure 3. Note that ungaging is really just like a physical change of basis, it seems, meaning there is a way to make these detectors work with both a gauged and ungauged state. This process allows us to take data which was previously non-local, information stored about what is happening between multiple erroneous anions, to local information, which can be then used to determine if we have found all the errors. Note that although information about the computation is stored non-locally between pairs of computational anions too, ungaging does not measure or interfere with this information because the decoder guarantees an erroneous excitation cannot propagate to another anion before it is caught. Only one computational anion is ungauged at a time, meaning the non-local computation is not touched. It remains outside or like just on the boundary of the ungauged region. In any case, panel B illustrates this whole process from delaying errors, which is what we talked about, all the way out to re-gauging. I would also like to touch on figure 4, even though it's in the appendix, since it shows the vertex and plaquette notation for stabilizers that came up a lot in my research, so I believe y'all deserve to know about it too. See, theoretically speaking, what stabilizers are is a way to check whether something has changed, some error has occurred, or something um is not how we want it to be. It's an operator that gives back the thing itself, kind of like an identity operator. And figure 4 panels A and B show two types of stabilizers based on two types of errors that can occur. Eta anions corresponding to electricity, kind of, and mu anions corresponding to magnetism, kind of. Remember, anions are just excitations, and depending on how they disrupt the computational anions on this lattice, they will violate stabilizers in different ways. For example, this vertex stabilizer is written like this alpha U thing. And with the sigma x operator being defined as flipping the state of the qubit while preserving the qubit. So qubit is 0 and 1, qubit is 0, 1, 3. I presume the Hermitian operator doesn't actually do much, the sigma x operator, and instead acts solely on the qubit. I didn't see it being like clearly stated how this operator acts on these sigma operators as like you see here, but that's only for like conjugating when there's both the normal operator and the conjugated K operator. So my guess is as good as yours as to what's going on there. But again, like I could be missing something. Sigma z, on the other hand, is defined like this, and we're allowed to have negative signs as a treat. Yeah, we are allowed to have like 0, 1, but we're also allowed to have 0 and negative 1. Um, right, the only place that we can't have negatives as like a treat is where like global phase matters, and this is in the stabilizers themselves. They cannot take something to its negative counterpart. Otherwise, errors that also take something to their negative counterpart would be ignored. Panel C and D of this figure involve the Q-trit system. Frankly, I am not even confident, even I am not confident enough to explain this. They're raising operators to the powers of matrices slash other operators here, and I have no clue why. Like, if you can make sense of it, I'll leave it up on the screen for you. There's definitely more mathematical stuff in the paper, such as operators commuting and the proofs that their methods work. This is a mathematical physics paper, after all, which is why it is so incredibly dense. Like, what is happening here? Yeah. But again, like I don't understand the proofs or the mathematical stuff. And I will point out in figure 9, though, which shows the maximum length in space-time that an error has to go through before we are confident it is corrected. This Q is an arbitrary integer greater than 1, but its choice has practical considerations with how separated to make the computational anions. Right? If we make this smaller, we can make this distance d smaller as well, but we would need to have more better stabilizers and detectors that can correct errors quicker. Right, and specifically, we want the computational anions to be far enough such that the error cannot propagate to another one before it is caught. Again, space and time are the same thing. Anyways, moving on to the further questions. What does this change? This is one of those huge if true kinds of papers. If this decoder is successfully implemented experimentally, and the paper's claims that about the fact that it works are proven true, then it could be the holy grail of quantum computing. From what I can tell, of course. In all seriousness, though, in all my research, topological quantum computing was speculated to be fault tolerant and was a major avenue being pursued. So, if there aren't any major caveats to this approach, I think this might be like a huge breakthrough. Again, I don't know. I don't run in these papers, in these spaces, but my rule of thumb is the shorter the title, the more significant a discovery. Further directions of research. Gosh, somebody please give these people money to implement their approach. It'd be so cool. Gosh, somebody please get them published in a journal so this paper doesn't get buried in the thousands upon thousands of papers submitted to ArcSiv each month that I also have to sort through for shortlisting, which is why I highly recommend you give me papers. But I digress. Those are my thoughts on this. Also, interestingly, there was a paper uploaded on to ArcSiv on a very similar topic just this March, like just a few days ago. And also, I think another one also uploaded in March. I might cover it in the March recap, or I might cover it in a follow-up, but I will link one of them. Overall, I do just want to look more into the maths of this because there is a lot I didn't understand, as well as I would be curious to know what logistical considerations need to be taken when designing algorithms for this kind of quantum computer. Since I did read in a paper linked in the description that some states could not be computed with this braiding approach, but of course, if this becomes a viable approach for fault tolerance, then algorithm designers will get around that for some specific purposes that quantum computers can be used for, right? We don't need universal computation. We don't need universal quantum computation in the same way that we don't need a Turing machine to make websites. And I make websites, like I can speak on that, I think. Yeah. Another general problem is non-zero temperature. It is still an open question of physics whether topological order, aka the non-local states that carry information in this paper's setup, can be preserved at non-zero temperature. At sufficiently cold temperatures, it may be possible to have relative stability, but long computations may still be impossible until we figure that out. Awesome. Um, the final and fifth paper. Wow, this has been really fun. The skeletal trap, mapping spatial inequality and ghost stops in Ankara's transit network by Eflonats Kansan. I'm not sure. An independent researcher, by the way. So anyways, I would like to preface this by saying, remember that poll I did asking if y'all would slime me out for talking about physics and society? This is the reason. I know I said January recap. That didn't happen. Anyways, this paper talks about the bus system in Ankara, Turkey. Specifically, it talks about all the things wrong and inefficient with it, arguing these inefficiencies stem from urban planning and structural issues rather than simply not enough buses. Specifically, the intro section of this paper describes some history that led to these structural failures, those being a so-called leapfrog expansion out from the center of the city as peripheral regions got connected, while the regions in between received less urban development. This is in contrast to how you might expect a city to expand, dubbed oil stain expansion, seemingly just by this paper. Like, I can't find anything like talking about that, but I mean, when have I been able to find anything? Where more peripheral areas like slowly become urbanized as the center develops. This, however, leads to the titular skeletal trap described. The sleepfrog expansion, where everyone who wants to get anywhere must go through the center of the city, meaning the transit there becomes overloaded. While you can expect central stops to be somewhat congested by virtue of there being more things people want to see in the center, Ankara's problem comes from the fact that there is very little mobility between peripheral regions, meaning even if you just wanted to go to a neighboring area, you would have to go through the center. Combined, This paper measures six different um, metrics of failure, mainly focusing on stops that are, for whatever reason, different from similar stops called anomalous and stops that change their characteristics depending on, for example, if it's a weekday or weekend, and these are called regime shift. For example, the kinds of failures which can be detected by the anomalous metrics are stops that receive significantly different usage compared to similar stops, perhaps ones with similar population density, though I'm not sure. Anomalies along all metrics are detected using a mathematical model because stop level usage data is unfortunately unavailable. However, root level usage data is used to then find so-called ghost stops, which receive very little usage, and these stops comprise 67.1% of the total network. Please don't laugh at that figure. It's actually like a really major problem that more than two-thirds of the whole network are just ghost stops that don't get written and don't get service. So don't laugh at the number. Thank you. Also, I want to note, this paper appears to have originally been written in Turkish, and all the sources are in Turkish. So for this paper especially, I ask anyone who knows better than me, perhaps somebody who knows Turkish or who lives in the area, to please correct me in the comments if I'm getting something wrong. All right, concepts. Kinda. Not really concepts. So first, data on where the stops are is taken from Google Maps and their locations confirmed with data from OpenStreetMap, which gave us 85.7% of all stops together. Um, what? That's wrong, which gave us 75.7% of all stops. I think. Yeah, it's 75%. Huh? Yeah, okay, it's seven. Okay, yeah, like this, the Google Street Maps API, plus the OpenStreetMap integration API together gives 75.8% of all stops. The coordinates of the rest were calculated using interpolation. The paper also states this interpolation is weighted, meaning there was a way to tell where the next stop should be. Interpolated, like which stop it should be closer to, but no details on this were given, unfortunately, that I could find in the paper. Maybe it is in the GitHub repo. I don't know. I'll have to check and put that down as a correction. Woo! Yay. After having these stops, their usage was calculated based on root level occupancy data and a model that assigned a higher probability to a stop connecting to many other stops slash routes would be used more. Look, this might seem like circular reasoning given that the paper states the failure of the transit system is due to its structure, but really it's only intuitive that stops that have more routes would, going to them and going from them would have more people ending up at them. In any case, how the passengers are distributed is calculated by first determining the connectivity of each stop in the network. This is calculated as the number of unique routes passing through a specific stop. Interestingly, the paper states for central stops, this can be as high as 84, which is a pretty high number. So high in fact that I originally thought that like it might be like a combinatorics thing where like every stop to every stop was counted separately, but that number would probably be even higher if it was due to combinatorics. So, and also that gets disproven later. So, yeah, whereas for stops further from the city, this can be just as low as one. Just one. Take it or leave it, I guess. The route connectivity is then calculated as the sum of these scores. This is used to calculate the weight of a certain stop by dividing that stop's connectivity score right here. Yeah, by dividing that stop's connectivity score by all the routes that connect to it. So, like to, okay, my English is not Englishing right now. I should probably like work on the run-on sentences. This is used to calculate the weight of a certain stop by dividing that stop's connectivity score by all routes that connect to its total connectivity scores. This does guarantee a percentage-like value since the connectivity of a stop will always be smaller than the total connectivity of the route it's on. And this actually just proves what I said like about the combinatorics thing. Right, data can often be surprising, but also like as a sanity check, a route consisting of just two stops that has the weights for those two stops distributed 50-50. And this ensures that the next step, passenger distribution, gives sensible values of passengers per stop. Next, let's look at the specific algorithms for detecting anomalous stops with the help of Table 1. The first row, the autoencoder, asks whether or not how much a particular stop is used makes sense in context. From what I can tell, this is basically if there's a route with some occupancy, then there's a stop in the middle of that route that has a much higher or lower occupancy, the encoder metric will detect that. In general, this PCA exists to figure out, oh, sorry, and to figure out along which parameters there is the most variation. The isolation forest metric is what you might imagine when thinking about outliers. It stops that are highly isolated with maybe only one or two routes they're connected to while still having, for example, very high occupancy. Local outlier factor is what I talked about earlier, stops that are underserved relative to other stops in similar types of places, e.g. with similar population density. Lastly, we have graph-based spatial, which detects if two locations that are close to each other receive very different levels of service or usage. This feels like a good time to mention that because the stop coordinate data could not be resolved precisely. Everything is on a 1 km by 1 km grid. This is just one of the many data limitations in this study, but it does make for some pretty cool figures, as we will see. Oh, also, like this table 2 is regime shift, so embedding instability and daily clustering. We will get to this. Promise we'll get to everything. Well, not everything, since this paper also has a bunch of figures. But we will see the cool figures after we get through figure 1, which shows the population density based on the lights at night. Looking at this picture intently, it will come, yeah, so just look at this picture intently because it will come up on the test, aka in future figures, but I'll pull it up if necessary. Hopefully. I'll just probably scroll to it. Realistically. The leapfrog development is evidenced by these patches of much light, decently far from the middle of the city, with less light in between the center and the smaller areas. Figure 2 shows how the paper defines different classes of grid failure. Again, the 1 km by 1 km grid is used to approximate stops. This is what the 1 km by 1 km grids look like. So there's anomaly only in orange. Then there's regime shift only, which is stops that have behave differently depending on what day it is. The metric regime cluster is defined as whether a stop has the same demand service relationship every day, which is really a fancy way of saying if people use this stop the same every day, while regime embedding is actually really similar. I'm not fully sure how they differ, although regime embedding does mention frequency, so perhaps it's going to factor in things like if buses come and go at the same rate every day, which could affect the demand-supply relationship, or perhaps regime embedding is just more broad, whereas regime cluster is specifically only for the two cases of deficit and normal, as we saw in this table right here. Locations whose assigned cluster oscillates between high demand, low service deficit and low demand, low service normal from one day to the next, indicating that the system cannot commit to a stable classification. Cool. Now I have to find where I left off. Yeah, and for stops that are known to have less service, I don't know where. Also something interesting I noted while editing, because I do, contrary to popular belief, edit these scripts, is that this paper uses the same method as the one in the applications paper for clustering. It's called k-means clustering, and somebody please hold me accountable on this because I wanna make a video covering all the mathematical techniques used in papers, this paper, but also this recap, but also the previous recap, since that was like the Fourier transform themed edition. Anyways, Figure 3 is the beginning of visualizable data weirdness. This pattern of significantly lower usage on weekends is to be expected and is described as sawtooth. And while it's pretty consistent towards the end of the data set, there is this section in the middle that does not display it. This section around March 2024 that does not display it. This is not because people started magically going to work on weekends, but because these data point circles right here are show that there was no data collected for this period of March 2024, and hence these are just straight lines. Basically just linear, drawing a straight line from one data point to the next, which is really what happens everywhere else. It's just that it's smoother everywhere else. Anyways, there's also this huge spike due to all the data from the holidays being lumped into a single day. Not great, but we work with what we have. It's actually pretty interesting to work with limited data, something I've done before. But yeah, overall though, this figure shows that passenger counts hover around 90,000 per day, except for the summer months, I presume due to school. Anyways, this data nonsense is further illustrated in figure 4, which shows the occupancy rate / percentage for every day for the 20 routes that have the biggest variation here. 611 at the very bottom, for example, had its occupancy spike around late April, and this could be a quirk of how data was collected, or it might be that the responsibility of another route was offloaded to it during this time. All routes have also had almost what? All routes have also had incredibly high occupancy since around August of, yeah, since around August, except 102-1 at the very top, which had these swaths of almost 0% occupancy. Something similar is shown in some routes around January, fascinatingly enough, and this is noted by the paper to most likely be the result of no data collected, similar to these large areas of seemingly exactly 50% occupancy for the summer months in some routes. Like, it could be that these are just 50% occupancy, but the fact that there seem like exactly 50% occupancy with no change in color makes me suspicious that it might just be because no data was collected. Again, summer months, no school, but we still saw some variation in figure 3, so I don't know, do with that what you will. Next are all the figures which involve the map. There are many of these, so similar to the third paper, I won't be talking about all of them in detail. Figures 5 and 6 show almost the same thing, that being occupancy or seat utilization or how well the supply matches the demand, while figure 7 shows average demand, no, figure 7 is down here. Figure 7 shows average demand daily by how many people are getting on at specific stops. Not sure how they managed to figure that out with no stop yet level utilization, but perhaps using the mathematical model. Figure 8, on the other hand, is interesting. It shows so-called ghost stops, which are there but are both rarely used and rarely have buses coming to them. As you can see, almost all stops that are not somewhere along like these lines at the center, which are major routes, are ghost stops, right? Everything else was basically a ghost stop or at least underserved. Of course, there are some exceptions to this, like this patch at the bottom and this one at the very top. But what was surprising to me is this whole branch that, if you remember, had a lot of nighttime light activity, is full of ghost stops. And it's full of no stops, actually, as well. Um, right, if you remember back from figure 1, there's like a lot of light here in this patch on the bottom left, and this patch also like along this axis, but a bit closer to the center. But there's literally no stops or only ghost stops at like this very um, bottom left. Anyways, as you can see, I know I already said that. Not a single stop on this bottom left is in a ghost stop, and now feels like a good time to mention that the reason Ankar's transport problem got so out of hand is, and I'm referencing the paper here, I'm paraphrasing, that the government pushed for private transportation, so cars and taxis, which means the people near these ghost stops who could have benefited from them operating are either forced to take cars, which can be expensive, or just wait for the rare buses that do show up. And the paper describes this as time poverty. Although, of course, it's not just because of the ghost stops, things like congestion also contribute. And as I mentioned in the intro, a whopping 67.1% of stops are ghost stops. And on top of that, 19.8 are underserved, meaning there is slightly more demand and slightly more supply than full ghost stops, but that's still not good. I don't have to tell you that that's still not good when there's only a handful of stops that are green in this whole graph, in this whole figure. Anyways, figure 9 mostly just gives visuals for the metrics we talked about earlier, and actually I'm just now noticing how regime embedding and regime clustering, okay, since here it it states it changes in, oh, okay. It states it changes high daily geometric drift in latent space, while daily clustering regime shift is just categorical switching between operational archetypes. So I think what that means is embedding stability is more general after all. I think. I'm not sure. This is like worded really confusingly for me. I'm sure it's not confusing for you. It's confusing for me though, so I don't know. Read the papers. Please read the papers. I'm not going through this alone. Thank you. Yeah, okay. Yeah. Anyways, so autoencoder is mainly stops just outside main routes from what I can tell, but also in the middle of what I presume to be the main route since it's longest. These appear to just be stops that people get on at the most, since they coincide really well with the high population / nighttime light distribution from figure 1. Isolation forces predictably stops on the very outskirts. Right, as you can see, these ones that are scattered and that are not connected to any other 1 km by 1 km chunks. And also, interestingly, these two in the middle, what I think might be happening is that these stops are just so close to the main routes that people would just rather take the main ones, which is why which is that perhaps they get lots of service but not any ridership. Yeah, local outlier factor is really just stops that people use a lot, where supply can't meet demand, I think. While graph-based spatial anomaly is stops that behave differently from their neighbors, and this has overlap with the autoencoder, the regime, and also the regime shift embedding one. Yeah, so the regime shift ones basically indicate where the workers live, I think. I mean, we observed that changes in ridership basically correspond to whether it's a weekday or not, but I'm not sure how much that carries over to individual stops. Again, since we don't have stop level resolution of ridership. Lastly, we have figure 12, which shows stops that correspond to the different kinds of failures all the way back from figure 2, right? The anomaly only, the regime shift only, and the critical grids, which have both. Right, and importantly, for a grid to be classified as anomaly only and regime shift only in this figure, it needs to be anomalous slash regime shifty and at least two metrics. Critical grids are then on the intersection of these two types of failure, ones whose underservice is exacerbated by daily variability in demand. Interestingly, almost none of these critical grids are on the main routes except for this area on the center left, which is interesting. I thought there would be more along the routes, but again, like there's these really scattered regime shift ones, and there's also these anomaly only ones as well. So I don't know. I don't think it's like anything that would prove the conclusions of this paper. So I'm not going to dwell on it any further, and I am instead going to be moving on to the further questions. What does this change? Well, the nice thing about these kinds of papers is I don't have to do anything for this section. The application is obvious. If the government of Ankara locks in and implements the changes proposed by this paper, namely transit routes connecting areas tangentially without relying on the main stops, on the central stops, which as shown could not keep up with demand even if there was purely more buses, trains, etc. There. Demand responsive transit, which is like dynamic routing, is also proposed, where the same buses, for example, could service different routes based on the specific demand that day of the week, and thereby freeing up some buses, which previously contributed to inefficiency in the peripheries slash to the prevalence of the ghost stops. Though then again, the ghost stops are ones that don't get any buses to them, so I might have lied there. I made that up on the spot. It's not in the script, so I probably got something wrong. These buses could then be routed to areas with higher demand. Now, whether these changes will be implemented is of course debatable, but we can of course hope for the best. Oh, my voice just died. Yay. Yeah, we can of course hope for the best, especially considering that these problems are actively being pointed out on social media, which is what prompted this paper in the first place. So for further directions of research, honestly, I just like this framework. I think it'd be interesting to apply it to other cities, modify it, play around with it. Though, of course, there's a reason Ankara was the one talked about here, that being people are speaking out about the problems in its transit system, again on social media and in the news. One of the main limitations throughout the study was getting data, not only geographical data of all the stops, but also data on occupancy. What was available from the official city sources was patchy, as we saw, and was only recorded daily, meaning, as pointed out in the limitations section, things like peak hour congestion would be impossible to determine, hence making it harder to make specific strategies to optimize the system where buses should go on an hourly level. Again, this is the demand responsive transit thing. So overall, doing this with more granular and more recent data, since the data used in this paper was from late 2023 to 2024. Again, I don't blame this researcher for using like this data from 2023 to 2024. Research takes time. I don't, I don't know that because I haven't done any research. The closest thing I have done to research is the fact that I'm recording this on the 29th of March, even though it's the February recap. Um, so yeah. But now that this framework is developed and the code is open, if and when we get new data, I think it'd be much easier to run it through this framework and see what can be changed. Again, assuming we get the data. Awesome. And that is it for today. End matter. So, please give me papers. I don't wanna have to select papers again. Selecting papers is boring. This is the unscripted section, as you can tell. Okay, I said Arxiv has too many papers. Arxiv doesn't have too many papers. Arxiv just has a lot of papers that I cannot feasibly comb through. Like I tried combing through it for the previous recap. I really did. I really did comb through. Well, did not comb through. I just went off titles for the previous recap for all of the high energy physics ones for February, which was pain and agony, which is why I did not do this today, do this time around. I just really wanted to cover a physics and society paper, and I really just like fitted the anion paper to something which I would be interested in. I've recently been getting more and more into superconductivity, which is why slash strongly correlated electrons, which is why I chose that paper, but also because it was unrelated, well, except for the icing model thing, to the rest of the papers. So yes, please in the comments or email me. Email will be in the description. Um, Also come to the live stream. It'll be fun. I promise you. I promise it'll be fun. As you have seen in this video, I am capable of humor. So, and in a more unscripted approach, I think it'd shine even more. The humor, I mean, and my sheer beauty. Um, Also, like, please subscribe. I promise I won't waste your time. I upload like once a month. Well, hopefully, I'll hopefully be uploading more, but like realistically, I upload once a month. So it's not that big of a commitment. Just subscribe to me. In any case, thank you. See you in the next one, which will hopefully not be this late. I hope this was fun and or informative. I hope some of the graphs were pretty. I understand they weren't as pretty as the previous recap, which you still should check out. Um, yeah, I think that is it for today. Leave any questions you have in the comments. I will not be answering them because you probably know this material more than me. Literally all of my audience is, well, not all of my audience, but like most of my audience is in the 18 to 24 bracket. So PhD and university students, I presume, you will know more about this material than me. So just like, don't expect me to be helpful in the comments, but do give me papers. If you give me a paper, it's almost guaranteed, unless the paper is like genuinely horribly written, like prose wise, and it will genuinely be literal agony for me to read. Unless it's something like that, I can guarantee you it will be featured. So, anyways, thank you so much and see you next time.